Okay, we are going to talk about rotational impulse uh, and how it's related with what happens to the body on which this impulse acts. Okay, so if you haven't really watched this video on rotational impulse, you can do now. So what it is you may remember impulse from force impulse. When force is varying in time, we plot the force versus time, and then we look at the area under the curve. We get an impulse, or you can say force times time is the impulse of that force. Maybe you remember that. Uh, so a simple definition of impulse is force times delta t. If the force was constant, then that is a correct definition for impulse of this force during this time it acted, and we use symbol J for impulse. Okay, very similar thing happens in rotational impulse, where you take rotational impulse will be you take torque, and this is torque instead of force, and how long it acted. That gives me rotational impulse. If this is constant, this is the force. If not constant, then just like if it's not constant, you plot F versus T, and the area, this area gives you the impulse. Similarly, over here, you would rotational impulse will be the area under the curve that torque acted. If the torque is varying in a very complicated way, you just have a complicated area. Okay. Now torque may be, if you're looking at a net torque, sometimes the torque may be counterclockwise, some clockwise. So sometimes torque may be positive, negative, and we'll have an example of that. Okay. So you remember that if I and alpha were, I was constant, this was something we used for Newton's second law. Now, if things were changing, I alpha was changing, whether I was changing and alpha was changing. A better way to do it is to go through this impulse system. So you plot torque and you get a rotational impulse, which is the area under here. And we plot I alpha because these are equal, right? So at any instant they're equal. So this plot will look identical to that plot, and area under here will be equal to area under. But area under here gives me change in angular momentum. So whatever the angular momentum is that instance, minus angular momentum here. So that's how writing like that. We can write this as a delta L if you like. So area under here, which is related to the torque, is the rotational impulse. Area under here is change angular momentum, and they are equal to in magnitude. They're equal to each other. Now they're also equal to each other in the direction. If this was ended up as a net clockwise, this will be a net negative. If clockwise was negative, so this value will be negative. And if this thing after working out, you had a net counterclockwise, which would be the case in this particular picture, counterclockwise, here it will be also net counterclockwise. And so we write this as a vector equation. I haven't proven this, but you can prove that if you add up the torque, the impulses, all of it, okay, and from the external forces only, if you have more than one body, okay, in your system, say I have a this is a human body, I have this arm, my body is rotated. So if you have many parts to your system, you one part on another part, you don't take that torque, you torque from outside, say gravity. So you add up all the forces that are acting from outside the system, and you compute their net rotational impulse. You will see that will be a net angular momentum change of everything. This was a very similar thing when you did the impulse and momentum. So added up. So this was net. I should write down there as a net also. This was net, was related with changing momentum. This is another way to write second law of motion, which if you go to the momentum chapter, you will see explained more. Okay, why this is another way to write second law of motion. Okay, so I'm gonna just illustrate this with one example of how this thing helps us solve problems. So assume you have some system, maybe bicycle wheel or a bar or arm. It has a moment of inertia this much, and suppose it was rotating initially at this speed, okay, and now you have forces act on this body, so that when you compute the torque, net torque, you get this kind of picture. So like over here is a counterclockwise torque, and down here is clockwise torque. So you can say all of this is the net torque is counterclockwise, and this situation is clockwise. With our notation is counterclockwise positive, right? So this one is plus. I mean, this is what do you think is the way it's rotating? Think about it. This is a plus. So plus corresponds for us is counterclockwise, right? Okay, and we need to find at this point in time. At this point in time, it's rotating like that. So what's the omega f here? That's what I'm trying to figure out. Well, this angular momentum definition is angular momentum definition. Let's put it there. Angular momentum definition is I omega, right? So you can see that if I add up the net torque, if I add up the areas here, that will be equal to angular momentum here minus angular momentum here, right? So let me do this out, right? So this is the area, and then I need to add up this area. This will be negative, this will be positive. So this area turns out to be base and height multiplied by 2, right? So base is 3 seconds, and height is 10 Newton meter, and divide by 2, that's 15 Newton meter second. That's the unit of this, Newton meter second. Now if this will be it's just a rectangle, so height and width. Width is 2 seconds, and the height is minus 5 Newton meter, and that's minus 10 Newton meter second. So when I add, actually I have to subtract. So J net is equal to 15 minus 10 is 5 Newton meter second. This must equal to change angular momentum. So I will make this equal to I times omega at the final time minus I times omega times initial time. Well, I is not changed during this time. If it changed, I'll have to use different I's for different times, okay? But in my problem here, I appears to be fixed. It's a rigid body, okay? If you are a human body or some other things, it will be changing. Now, so this equation actually tells me this I and omega f. So omega f is unknown. I is 5 kilogram meter square omega f minus this is 5 kilogram meter square times omega I is 2 radian per second. See, all these writing units is really pretty stupid, you know. We shouldn't be doing that. Another thing could be is I could have taken I common, right? So this equation, it can be handled a little bit better than what I've handled, but let's not worry about that. So this equation will be 5 omega f minus 10 is equal to 5. So I'm going to just drop all the units. Writing all this extra stuff is unnecessary. So if I then on that side, so omega f is 15 over 5 is 3 radian per second. So I found it that net it is counterclockwise. So it's counterclockwise, and net torque is counterclockwise because there's some positive, some negative, but in the end I had a counterclockwise torque with a plus being a counterclockwise notation for me. So from 2 radian per second to 3 radian per second doesn't surprise me, right? Because it went up. I was rotating this way, and then I had more rotational impulse that way. So it increased the rate of rotation. Okay, I hope this example helped you, and this idea that the area under the curves have to be equal to each other, giving J rot rotational impulse equal to change in angular momentum. In the next video, we are going to have an application of this that's very important. So when this area, suppose, is 0, okay? So suppose this is all, when this area is 0, then this area has to be 0, right? Very trivial statement, right? That would mean that in those situations angular momentum will not change, and that's called angular momentum, principle of conservation of angular momentum. It's a sister principle of the principle of conservation of momentum, and it's a very important principle, and we're going to look at it next. Okay.